This is a archival photo I found in the New York Times. This was Ted Hood's obituary. Showed this picture of Intrepid, and you can see the boom vang track right there. Now this is a photo op picture. If you look closely, there's a guy with a camera standing on the boom taking pictures there.
Welcome to you who are here with us in person, and to you who are with us online, to the Charles River Museum of Industry and Innovation, and tonight's Tech Talk on the development of the ball-bearing Traveler and the 1967 America's Cup boat Intrepid. I'm Bob Perry, I'm the museum's executive director, and I first want to thank the Lowell Institute, founded in 1836 to provide free public lectures to the people of Boston, for their support of the museum, which is making tonight's event possible in person, and for their support of the GBH Forum Network that is managing the virtual delivery of this event. It's certainly not the norm for me to have my vocation, which is managing an industrial museum, intersect so elegantly with my favorite avocation, which is racing sailboats. But that's exactly what's happening here this evening. And at our core, we here are a museum of America's industrial history. And given our roots in the 19th century, we certainly lean more toward mechanical engineering than, say, electrical or chemical in terms of our artifacts and our exhibits. And one of the exhibits that our visitors tend to enjoy most is our fully functional antique machine shop, which is on your left. And it's got all full-scale machine tools that are powered by belts and pulleys, and that was a system that dates back to the days when water wheels were the source of energy to power mills like this. Mr. Alan Palevsky is himself a physicist and an accomplished sailboat racer, and he's here tonight to share his experience working in a machine shop nearly 60 years ago. 55 years ago, a machine shop that fabricated what was at the time ultra-modern racing sailboat hardware using cutting-edge materials. For Intrepid, the 12-meter yacht that in 1967 successfully defended the America's Cup title that had been held by the New York Yacht Club for well over a century by that time, and would do so again in 1970. Alan and I have been for many years now competing against one another at the Boston Sailing Center's Tuesday night summer racing fleet on Boston Harbor, which is of course how I learned about the absolutely fascinating piece of Alan's personal history, and that's what he's going to be sharing with us tonight. Coincidentally, the father of the Lowell Institute's founder was himself the founder of this very mill. His name was Francis Cabot Lowell, and he's the namesake of Lowell, Massachusetts, if you didn't know that. Before Francis became a textile manufacturer, however, he owned a fleet of clipper ships himself and also built and controlled India Wharf, one of the major 19th century commercial wharves on Boston Harbor, which today is the site of the twin residential high-rises that we know as Harbor Towers, and where residents just so happen to have an excellent view of Alan and me mixing it up every Tuesday night. Alan Palevsky grew up sailing on Great South Bay on eastern Long Island. He started by crewing for his older brother in the Blue Jay class in 1959. Is it that brother who's with you here tonight?
Yeah, my brother's here.
They graduated to the Windmill in 1965, and that boat was a Clark Mills design as the next boat up after the Optimus Prem. They took second in the Windmill Nationals in 1968. In 1974, Alan started racing the Tornado, the Olympic-class catamaran. He raced that class through 1988. In 1986, he was ranked 10th in the United States. He also raced interclubs in the Marblehead Frostbite fleet from 1982 through 1990, and finally, he's been evening racing Solings on Boston Harbor since 1981. He earned a bachelor's degree in physics from Williams College in 1973 and a PhD in physics from MIT in 1980. He spent 37 years at Raytheon and retired in 2018 at the level of director. His work at Raytheon was across many disciplines, including high-power microwave tubes, flat panel displays, and satellite communications. Since retiring, he's been consulting part-time in the electronics industry. He's also volunteered at Courageous Sailing Center in Charlestown, Massachusetts, helping maintain their boats. Ladies and gentlemen, welcome Alan Palevsky.
Well, thank you very much for showing up. I'm glad so many people showed up for somewhat of an esoteric, topic, but we'll go from there. So the presentation outline, I'm going to talk about some material properties as, the materials, as sort of a bit technical, the materials in the boats originally were wood and bronze, and then part of this talk is talking about some of the new materials that came in. Then, if you look at the 2 decades between 1956 and 1976, this is where there was a huge revolution in terms of a sailboat hardware. And there was a huge revolution. I'll go over what the Olympic classes were in 1956 and 1976. And the work I did in the 60s was sort of in the middle of that revolution. And at the time, as a kid, you don't understand you're in the middle of a major transition, but in retrospect, 50 years later, there were major changes going on in terms of sailboat hardware, sailboat sales, sailboat construction in those times. Now, this talk, we'll talk about a gentleman who nobody here knows except people from my hometown, and his son is here, a guy named Edmund Laviano, who was a sailor and inventor and was responsible for most of the hardware I'm going to show. In terms of the hardware, when I started sailing with my brother in 1959, there were no cam cleats on boats. There were just regular cleats. And then the cam cleats came along and he developed a cam cleat. He also developed a snap shackle for the 1964 America's self-defense. And then the ball bearing travelers he started developed in the mid-60s. And the big place that went on was Intrepid, which was the 1967 defense. And we'll talk about that quite a bit. There was an abortive effort on Columbia for a one-wire rope main sheet system. Then I'll conclude. But that's sort of where we're going to go here in terms of the talk. Now, this is materials that I'm going to be talking about. I have actually samples of these materials here in a tray and this same chart here, so you can actually pick them up and feel them. And in terms of the material, there's the density and the tensile strength are the important mechanical ones, but there's a metric called the specific strength, which is the ratio of the two. And the higher the specific strength, sort of the better it is to use on a boat because it's stronger but lighter. Then I have pricing and then the weight for the samples I have here. Now, if you go back in time, the only materials people had were oak, wood, and bronze. And then phenolic came along. I think phenolic was developed by the phone company for the phones, but then it became more general use. And in the late 50s, people started making sailboat hardware using phenolic. And then stainless steel started to come down in price. Aluminum became more useful. Titanium is quite expensive. It was only used in special conditions. As example, the Traveler for Intrepid. And after that era, carbon fibers came along. Now, if you look at the specific strength of carbon fiber, it's an order of magnitude higher than anything else. And that allowed the development, which is outside this era I'm talking about, of things like, hydrofoils and foils to get boats out of the water. So that's beyond, but I'm just saying, with the materials available in the 56 to 76, at the end of 76, you couldn't have built the type of hydrofoil boats we have today because you didn't have carbon fibers. So, we'll go from there. Next slide. So, I have a couple of slides talking about the major changes that went on between 56 and 76. The hulls. 56, all hulls were wood. By 76, there were still some wood hulls, but most boats were made out of fiberglass. The spars were wood. By 76, your spars were all aluminum. Now, in terms of sails, 56, it was Egyptian cotton sails. It was Egyptian cotton. It was the long fibers, so they didn't stretch out. And when I started sailing again in '59 with my brother, we had Dacron sails, but when we're out sailing in regattas, there were lots of boats in those days that still had cotton sails, and you could see the cotton, an older cotton sail was sort of brownish, and the Dacron was this nice white. And the other change was in the spinnaker. The spinnaker was made out of nylon, and it had a ripstop weave, which everybody knows today, but it was important. So if it started to rip, it minimized the rips. And today, you know, some racing and most day sailing, it's all Dacron, but the top racers have more exotic sails. In terms of the fittings, most of the fittings were either brass, bronze or wood. And then by '76, you didn't see bronze on boats anymore. It was stainless steel, hard plastic, and aluminum. As I said before, cam cleats. There were no cam cleats on our first Blue Jay. The spinnaker had no cleats at all. The jib sheet was a cleat on the centerboard trunk, and the skipper had to hold the main. There were some travelers on boats, but it was slides with stops, and you couldn't adjust them under load. In terms of line, it was manila. You can find manila in the hardware store. You never find a manila piece of line on a sailboat anymore. And for fancy docking lines, people had cotton. It was twisted. None of it was braid. By '76, it was all Dacron and nylon braid. Shock cord, it was uncommon. By '76, it was common. One of the other things, most times in racing sails, on your main and jib, especially on the front of the jib, you'll have a little window, and you'll have telltales on each side to see you got the adjustment is right. We didn't have that in '56 or in '59 when we started sailing. Somewhere that transition occurred where people started actually putting indicators. In '56, most boats did not have stainless steel rigging. It was galvanized steel with zinc that was greased. One of the innovations on our Blue Jay in '59 was stainless steel rigging. And by '76, all standing rigging was stainless steel. There are no roller furling jibs. And this is more to the yacht club where I grew up. The sailing lessons were taught in Cape Cod Knockabout, old wood boat. In '60, '61, Cape Cod came out with the fiberglass Mercury, which had flotation tanks. That was a huge deal. And Mercuries are still sailed on at community boating. That boat's still around. Now, in terms of life jackets were the K-Pock, big orange things, quite bulky. And by '76, we had air-filled and synthetic foam, much easier to wear. Foul weather gear, I had to look this up. I don't remember, but, I got a timeout here, excuse me. Foul weather gear was canvas with linseed oil and paint. That's what foul weather gear was. And by '76, we started to have breathable fabrics and dry suits. Nobody wore sailing gloves when we started, and everybody does it now. And the pumps. The pumps were this. The pumps were a galvanized steel pump with a wooden handle and this leather pouch at the back, which this is all worn. You have to let it swell up to make the vacuum seal against the galvanized. So you had to pour water in to prime it, you had to prime it hard, and it didn't get much out of the bottom. It got to a point where you had to sponge the rest. And that galvanized steel pump was what everybody had. And I think it was in 1960 or 61, what's known as the Thirsty Mate came out, which is pretty much the pumps we're used to today. And it was like a revolution. It was a huge change. And it was hard to find those pictures even. And I tell people a bit younger than me, well, remember the galvanized pumps? And it's like, what are you talking about? So, and it was my job in the Blue Jay, sailing downwind, to pump out the boat from all the water we got upwind. So I was, as my brother was steering and the other crew was flying the spinnaker. I was in the back working this damn galvanized pump. So, to boats, building boats. Boats were wooden, and a lot of times people would get together and do group builds. There were some factory built, but a lot of fleets were group builds of plywood boats. And by '76, that was gone. Most fiberglass boats were factory built. Now, in terms of catamarans, the Tiger Cat, which was one of the first production cats, came out with 60, but the Hobie 14 came out in 67, the Tornado 67, and the Hobie 16, which swept the country in 71. So by the 70s, there was a lot of catamaran sailors. Self-bailers, there were none in 56. Elfstrom came up with those first self-bailers sometime in the early 60s, and by then, almost all racing boats had it. In terms of paint, all paints were oil. And by the 70s, people were coming out with the 2-part polyurethane Emeron high-quality paints. Bottom paint was copper bottom, horrible stuff. I remember putting it on, and then my father having to clean me with acetone to get all the copper bottom out of me. That's why I am what I am today. And by 76, various synthetics. Now these are sort of more general things, but paintbrushes were all bristled. You had to clean them all afterwards, and now we have nice disposable foam brushes. If you ever worked fiberglass, you know how nice it has to have the Sureform tool for making the rough cut. That came out in 56. The Boston Whaler, which we all know and love, came out in 58. The Windsurfer was patented in 68. Kevlar came out in 71. Velcro, I don't know how we lived without it, 1955, and super glue in 58. And so going through this list, it's sort of a sailor from today would find a boat in 56 quite antiquated, while you put a person on a boat from today and a boat from 76, except for the electronics and some of these more modern sails, it'd be quite familiar. So there was this 20-year period where there was just a huge revolution. Now, also in terms of the Olympic class boats, the number is the number of crews. So there's the Finn, the Sharpie, the Star, the 5.5 meter, and the Dragon, all wood boats, no trapezes, no catamarans, and the Sharpie was actually gaff rigged. 5.5 meter was a development class, all other was one design. By 76, the Finn was still there, but now there were fiberglass. The 420, which is still in the Olympics, was there. The Flying Dutchman was there. Tornado was there. The Tornado's been replaced by the Nacra. The Tempest was there, and the Soling was there. Soling was there until 2000, and they're all fiberglass hulls, all aluminum spars, 4 of them with trapezes, 1 catamaran, and all the boats were one design. So again, that change was reflected in that. So that's sort of the milieu I'm going to be talking about. Now, Wally Ross is a name a lot of sailors know, and I knew him growing up. He lived in Bellport, where I grew up, and he's got a Wikipedia page because he was an important person in terms of sailing. He was a president of a company called Hard Sails and Seaboard Marine from 54 to 74. And he made the sails for a lot of small boat champions and 12-meter classes. And his major innovation was the radial spinnaker, the spherical spinnaker, and his webpage says the ball-bearing traveler, which is not correct. But if you out on the water or in a fleet one day and you see all the boats coming downwind, you see all those colored spinnakers, that's Wally Ross. Wally Ross was the one who figured out how to cut the nylon spinnaker and to make the spherical spinnaker. There were some boats, old classes on Long Island that had, I think of one of the Seaford Skiff, that there was a big fleet out of West Hampton, and they had these spinnakers, and they were like white triangles. No shape, no nothing, and that was the prior generation of spinnaker. Now, That mistake in his Wikipedia page is sort of prompted me to think about doing this whole event, okay? So, Edmund Laviano, who a lot of this talk is about, also of Belport, developed the ball bearing traveler. It was marketed through Seaboard Marine, the hardware division of Hard Sails, of which Wally was president. And this may be the cause of the confusion. And part of the reason for this set of talks is to set the record straight in terms of Edmund Laviano. Now, the other thing in terms of just, when people do these Wikipedia pages, they say the 60s. In fact, the 1958 America's Cup boat Columbia had a hard spherical spinnaker. And in 59, which wasn't the 60s, our Blue Jay, we had a hard spherical spinnaker. So now, I'm going to talk about Edmund Laviano. So Edmund Laviano, half a generation older than me, grew up on Long Island, sailing in Great South Bay, same place I grew up. Now, there's some interesting history. His grandfather made a fortune during World War I, which had the machines that spun gold braid for officers' uniforms. And World War I was the last time officers had gold braid uniforms. So his father made a fortune. And he built a mansion on Howells Point in Belport, which had been extended out of the bay, so it was landfill, with landfill from the Intercoastal Seaway, which had been built through Great South Bay. And Edmund was one of the better sailors on the bay. He dropped out of law school, much to his father's upset, didn't make his father happy in the early 60s, so started a company that makes sailboat hardware, and he repaired and upgraded sailboats. And he set up his shop at his grandfather's mansion where he lived. So in 1959, the first year my brother and I sailed the Blue Jay as midgets, they divided the fleets into midgets, juniors, and open. And the midgets, I think, were 14, the juniors were 18, and then above. He and his wife won the Great South Bay Blue Jay Open. And he became, in that small town, the go-to person for racing. He was the local expert. And so I started working for him in 1964 when I was in 8th grade. This is before OSHA. I violated every child labor law probably. My parents were happy I wasn't getting into trouble. And until I graduated from high school. And this talk is comprised of my memories of that era. And again, repeating, the time period I worked for that company was in the middle of the aforementioned 56 to 76 transition. Now, his first invention was the C-lock cleat. It was introduced in the 62, 63 time frame, and it was a, this is a boat show model of that cleat. It's 2 times. And it's a roller bearing design. So it's an injection mold plastic body with an injection mold roller on a spring, and it's on an angle. So as you pull the line through it, it opens up, and as you let the line go, it cleats. And so it's easy to engage, and it was easy to disengage relative to existing state-of-the-art cam cleats at the time, which were made out of phenolic, and I'm sorry, I couldn't find one, okay? And this is the boat show example, and he built a machine to custom wind the copper spring. And he sold this through Seaboard Marine, the division of hard sails, and it actually became class legal on the Sunfish. Now, this is the early days of injection mold. People, injection molds everywhere now, but in the early 60s, it was sort of new process. Most stuff was made out of metal. And there were issues with voids in the injection mold, so he had to screen them on a pneumatic pull press. So the first job I had at his factory was taking one of these things with nothing in it, putting in to the pneumatic puller, pressing the foot pedal to pull it apart, and then let it go, and if it broke, I threw it in the garbage, and if it was good, we processed it. So that was sort of our destructive testing. But the interesting thing above and beyond that design was the multiple configurations. And this is, if you look at this, that's the basic design in the upper left, but then he marketed a whole variety. One with a shackle, a feed on a swivel with a swivel and a becket. And that's called a becket, and all sorts of different designs. And in fact, this one here, I should point to it, had 2 cleats on it. One cleat for the main sheet and one sheet for the traveler. And when I had my first tornado in '74, that racing boat, I had one of those on it. But now if you go to any of the sailboat catalogs, major vendors, you'll see the basic cleat and all these other combinations. But to my knowledge, he was the first one to realize you had to market not just the cleat, but all the different permutations and combinations, how it's going to be used. And that was as big an innovation, I think, as the cleat itself. So now I'm going to step back a bit and talk about material. Again, as it relates to the next topic, which is the snap shackles. Most of the stainless steel used today in the marine industry in the 60s was 304, non-magnetic, not heat treatable. Today, 316 is used, which has 2% molybdenum for corrosion resistance, and I have them listed at the bottom. However, 17-4PH is a stronger stainless alloy and was relatively new and rare at the time. It's magnetic and heat treatable for added strength. That is, you purchase it, you can process it to be softer, and then when you're done your machining, you can make it harder. However, even in its soft state, it's more difficult to machine than 304. In its hardened state, it is 2.7 times stronger than 304. And in 67, its usage was quite limited. Now I'm going to talk about it in 2 products below, the Constellation snap shackles and the needle bearings on the defendant blocks. But if you look at it, I've listed the 304, 316 on the top, and 17-4PH on the bottom. And on the tensile strength and hardness, you have the soft and hard, and you can see it gets very hard. So after it's hardened, it's quite hard. It's very difficult to machine. Now, Constellation was the 1964 defender for the America's Cup that won. And this is sort of on his entree into the big boat market was the Constellation shackle. And it's used on the foredeck for halyards and sheet attachments. Load capacity of 17,000 pounds. And those loads aren't continuous. Those loads occurred when, like, the spinnaker snaps or the sheet snaps. So, it's instantaneous load that was breaking stuff. Now, an important part of this is you think about snap shackles, the hinge is at the top. So when it opens up, there's no place for the line to foul. Now, I should have shown in the presentation the more conventional hinge where the hinge opens up and the hinge has a little divot in it. Sorry, it's not here. But that's a non-fouling design, and even today you find some that use this design and some don't. And he had developed these for Constellation. He had built a bunch, but for me, that was the first machining job I was assigned. My job was to assemble these shackles. And now I'm going to have some eye charts where I'm actually going to talk about, since we are a place of manufacturing, what it took to make those. So the snap shackle was designed with the 4 major parts, and I grabbed the one here. The 4 major parts. You have the body, the closure, the attachment here, and the pull pin. Now, the first three parts were made, were made by an outside foundry by the lost wax method. And and Edmund had to make the machine negative for these parts. Now the way this works is the lost wax method is the foundry uses the mold, which is a negative mold, to make the positive wax. Then that wax is then surrounded by ceramic, and the ceramic is hardened. And then the wax is removed by steam, and now you have this ceramic which you can pour your molten stainless into. Then the ceramic is chipped away and the part's delivered. Now in fact, this lost wax method is the same method the ancient Greeks used to make their bronze statues. So it's been around a long time, okay? Now, the parts had rough holes, had a rough hole for this attachment, and had a rough hole for the pull pin, and had a rough hole for the screw for the base. So my job was first to get rid of any remaining ceramic, because when they came back, the foundry didn't remove all the ceramic, and if you have a ceramic in there and put a cutting tool against it, things don't work very well. The next job was, there was a tap to screw this into, and that tap writing operation was the most difficult part of the operation. And if I broke a tap off, you couldn't get it out, it was a scrap part. And so we had to keep this was the day before coatings on tools, so we had to constantly sharpen the tap. And one of the contract machinists helped me set up a fixture, so instead of having to use new taps, I could sharpen the tap on the grindstone there. So then, the pull pins, this part was made on a lathe, and then we made a custom spring also on the lathe. Then the opening arm was attached to the body, and now the important thing was making sure this hole was nice and straight. So we drilled down and then ream in so it was all co-aligned. Then the parts were ready for heat treatment. Parts would go out for heat treatment, come back, we'd screw this in and weld it, weld that. But during the heat treatment process, things move a bit, so we had a very little, a reamer, just a bit, to re-ream even the hard metal. Then came the fun part. They were pull tested. So he had fabricated a pull tester of a 1 foot wide, 5 foot long I-beam with a World War II surplus B-17 landing gear hydraulic cylinder hooked up to a pump. And we put the 10 shackles together, put heavy plywood over them, run the oil pump from across the room, and then crank up the pressure. And we got breakage. And when the breakage was, it was a lot of noise, and there were big dents in the plywood. But that was fun, you know. And then the parts that made it through were X-rayed and Magnaflux. Those are techniques still used today. And then the castings were rough, and then we go and shine them up on the on a wheel with some grit. And the last step, we'd put them in nitric acid to prevent any surface rust, and then ship them. So that was my life, you know, introduction to machining. And here is one of the actual shackles. This is the original Constellation shackle. Now this one was rejected because I think somehow when they put the pull pin in here, this hadn't been heat treated properly, so you see it got stretched a bit. So this was not delivered, and his son had this so I could show. But this was, you know, a major breakthrough in terms of lightweight strength design. Now, we don't have the molds of the original snap shackle, but up here you can look at the molds of a smaller design. You can see the mold here. You can see the You can see the pour point for pouring the material in, pouring the wax in, and here's the design you can see that fits in the mold. So that was, the snap shackle. Now the next thing was he started what I call the small and medium ball bearing traveler. So the first ball bearing traveler he developed was for smaller boats and wasn't the big boat that ended up one on Intrepid. Now, because of his experience with the injection mold on the C-lock cleat, the last thing he was going to do was make a traveler injection mold. Today they all are, but the injection mold materials weren't that reliable in those days, so he went to an all metal design, all metal construction. So here is a picture of it, and this is sort of, we have no mechanical drawings, so I sort of drew this by hand of the car section. And the design was a upside down U-shaped car on an I track, or if you want to call it a rotated H track. And then you had, that was aluminum, that was aluminum. So the car and track were aluminum, and these were just extrusions, so they were easy to fabricate cheap. Then in each car, there were 2 pins on each side. You can see the pins. And these were press fit into the car, and these holes weren't drilled, they're actually punched. So there was no drilling operation. And then on these pins rode a ring, stainless steel ring, and then 6 stainless steel ball bearings. So you had 4 of these on each side. And that configuration, you took it up, down, tilt, or twist, and you always had the ball bearings or the rings engaged, so it was low friction. Now to make that, these extrusions were bought, but he had to make the stainless steel pins, the stainless steel rings, and these are the control lines on top. I don't show in this schematic. He had to make the Delwood rings for that. Now the card had patent pending on this, stamped on the side, so I assumed there was a patent. Years later, I looked up and there was no patent. So people copied it later, but there was actually no patent on it. Now, this automatic lathe was another machine that we worked on, and this is sort of relates to the state of the art of machine tools in those days. This is a picture of what that automatic lathe looked like. It was a cam-driven device, and this isn't the one we had, but it's the same thing. It was a German machine. Again, there were no CNC machines. Automatic lathes were cam-driven. That is, these cams at the bottom would turn and move the tools in and out or up or down. So the cams were hand ground to control the cutting speeds. So the sequence for making the rings was the jaws would open, the stock would move to the raw material would move to a stop that the cam had put in place, the jaws would close, the stop would move away, and there'd be a cut of the outside diameter. There was also a rough drill cut through the center hole, and then the tailstock had a drill and a reamer, and there was a pneumatic switch that moved one up and down. So you first did the drill, it backed off, then the reamer went in, drilled, came out, and they cut the part off. Now the stainless steel chips, again with the tools in those days and the limited control with the CNC machine, the chips would not break. So we had to stand there and pull the chips out as the machine ran. So, so that was an important, tool for making the prime parts for the Traveler. Now, he ended up essentially with 4 products lines there. This is the first one was single car, first, small boat, single car, small boat, double car, and this is what I used in the Tornado in the 70s. And then he went to a bigger track, bigger car, medium boat, single car, and I call medium boat, double car. Now these are my terms, small, medium, and then I call this one the one used on a Defender, large boat. Now, so this is really a first. The first prototype design was built in 65, small car, small track, and it was built for Peter Page, who was a local resident, who was a major investor in hard sails. He had a new Narascatuck built for his sons. Now, a Narascatuck was a centerboard low draft hull with a starboat type rig, sliding backstays, that was used on Great South Bay because Great South Bay had a lot of shoal water and you could only sail stars in certain areas. It was a big fleet in those days, and the promise was it would be ready for race week, the end of July. Now, Edmund, one of his drawbacks was he was always doing things at the last minute. And so we were machining all day, and the night before the race, 9 o'clock at night, there I was underneath the deck, holding the nuts as he was screwing the damn track down. And then someone else in the boat, I remember this, was dropping cigarette ashes on me because I was there, the little kid with the head underneath the back deck and my legs sticking out. So, I have memory of them dropping cigarettes on me, cigarette ashes. So, this was really a revolution because with the ball bearing Traveler, one could now adjust the angle of the main sheet under load. That is, you didn't have to have a loose main sheet and then adjust some slider with friction. And this was a major improvement in sail trim control, and anybody who's sailed a boat in puffy days, the puff hits, you just want to drop that Traveler down. And you couldn't do that until this was available. Now, originally, it was for the Traveler, but then other hardware uses became apparent. By curving the track, it was possible to make a self-tacking jib system. And this happened in the Olympic Star class, Star, Tempest, and Soling classes. And this was, again, a major breakthrough in terms of sail handling, is you didn't have to trim the jib on each tack. And another use was actually they used the double car systems for the fore aft adjustment of the side stays. That is, the stays didn't go right to the boat, they went to the car was on the deck, and then you could slide them. And I remember vaguely some classes outlawed this because people were sliding the cars too far forward, the masts were falling down. The other thing was a big U-shaped track was made for one of the early America's Cup catamarans because the main sheet, the boom, you had the big wide boat, you could make the big U and then the Traveler would follow the boom. Now, today, ball bearing Travelers are ubiquitous. This design has been sort of obsolete by more modern designs that can utilize injection mold plastic, stronger, more reliable. But again, most people aren't aware of the history of this development, 50 years ago. Now, this is where it gets interesting in terms of the 12 boat, or the large boat, 12-meter design. So the small boat design Traveler, he felt couldn't be scaled to the large boat. And I think it was true with the materials that were available in those days. So the stronger requirement merely made you couldn't have an aluminum car and aluminum track. You needed an all stainless steel design. So the design was a T-track, where this is the T, and this is the car, and then you have ball bearings there, and you have what these are outside called return races that return the ball bearings around here. And so you have 4 sets of ball bearings and 4 return races. And again, up, down, tilt, twist, no matter how you do that, the ball bearings were engaged. And he told me when he looked for a patent, he couldn't do it because years ago, elevator designers had patented such designs. Now, and the first contract was in '66 for a yacht called Good News, and the second contract was a yacht called Windward Passage, and the original design was a stainless steel car, stainless steel track, milled out of solid track stock. So making the track was a big deal. But the return races were made out of phenolic. Now, at this point, the neighbors complained about trucks coming into a residential neighborhood, and I was sort of caught in the middle because the neighbors 2 houses down was best friends with my mother, and she complained to me about the industry going on in AA zone neighborhood. But at that point, he moved to an industrial zone. He also, for the new machines he was buying, he needed 3-phase, and there isn't 3-phase, 3-phase 220 in residential area. So he moved his shop to an industrial zone. He purchased a vertical milling machine, large turret lathe, other real equipment. He hired a full-time machinist and employed timers. And at that point, I had exposed beyond his to some real skilled people. And one of the ones was an older German who apprenticed in the 20s. And retired, spoke with a heavy German accent. And he was sort of, worked a few days a week on difficult jobs. And at one point, I forget what the part was, but it required sort of a complicated shape. And Edmund was trying to set it up in the machine, and the German machinist said, no, just give it to me. And he took this part, a piece of metal, and he walked out to the grindstones. And he just, by holding it in his hand, just shaped it. And it was probably within 5 mil accuracy. I don't know, it was incredible. And we sort of were stunned. And he said, well, when I was a teenager first apprenticing in Germany, the first 2 years were at the grindstone. You didn't get to work the machines until you could grind. Now imagine trying to do that today. Grind and file, yeah. Now the second one was a technician from Grumman. Grumman Aircraft was on Long Island today, and he was again, sorry for the timeout. He moonlighted there on Saturdays. And he did specialized welding. Now I don't know if any of you here have ever done heliarc welding, familiar with it, but it's you have a tungsten tip, argon coming out, you heat the part, melt it, and weld it. Now, I did some stainless heliarc welding, and stainless steel is pretty easy to weld because counterintuitively, stainless steel doesn't have heat conduct very well. So when you make a puddle, the puddle's small, and then it's very easy to control. Now the art is doing aluminum. Aluminum has a very high heat conductivity, so when you start welding, the whole part gets hot, and if it gets too hot, your part the whole thing melts. So one day, he was doing an aluminum job, and he said, I can heliarc weld 2 pieces of aluminum foil together. And we all laughed, and I think my boss even made a bet with him, a bottle of liquor or something. He came in the next Saturday with the heaviest aluminum foil you could find, laid them next to each other, and and welded. It was, I'd never seen anything like it. But I'm just saying, there were, skilled blue-collar workers who were really good at what they did. And I learned a lot from them. So, now, Intrepid. This is America's Cup boat, 1967. It was built for the America's Cup defense. It cost $1 million, which is close to 10 million these days, and it was a record amount of money for the time. Sparkman and Stevens design, built out of wood, City Island, New York. And we actually drove hardware from Long Island to City Island for installation. The skipper was Bus Mossbacher, one of the leading American sailors at the time. And Bus had won the 67 defense skippering Weatherly. But the word was that Weatherly was actually a slower boat than Gretel. And luckily, Bus just outsailed them. Now, the New York Yacht Club wanted to make sure that did not happen again. So this was the super boat. 3-section mast, bottom 2 sections aluminum, top titanium. Stainless steel rod rigging with an aerodynamic T-drop cross-section grind. So the stays weren't wire, they were aerodynamic shape. Titanium boom, it had this unique dual rudder system, a regular spade rudder, and a trim tab on the back of the keel. I'm not 100% sure of this one, but I thought they used depleted uranium instead of lead on the keel, 1.7 times denser. The winches were located below the deck. Now, I think they changed the rules that you couldn't do that later. The sails were by Ted Hood. Now, the last 4 things were the ones that the shop was involved in. A ball-bearing traveler, boom vang system, the general blocks, which I haven't described yet, a custom head stay to the deck fitting, and a set of Constellation shackles. Now, the last one I just built, so I'm not going to talk about much, but that's my contribution to Intrepid. The custom head fitting I have no information on. I know the German machinists spent a lot of time making it, but I have nothing to talk about there. And so we'll talk about, in detail, the next 2 items. So the traveler, we talked about the big boat traveler, the main sheet traveler with cheek box to the control, with a control line is shown in this picture. So here's the ball bearing traveler, the track, there's the car, there's the fenelic, and these were custom cheek blocks for the line to control how far the traveler went. Now the turn races were fenelic. Edmund told them not to grease it, but sometime during the summer, he got a call that the traveler had exploded. He went down there and somebody had decided to pack it with grease. Caused the ball bearings to jam, the fenelic to break, balls fell out. So he had to replace the return races and reload it. Now, in 67, it was fenelic. In 70, when the boat ran again, the return races were upgraded to a stainless steel casting. And that actual traveler is what we're showing here today. You can come look at it after the talk. So this is the actual traveler from Intrepid. Now, the traveler track, as opposed to the original ones, were made from titanium to reduce weight. There was one foundry in the US that could extrude it. We ordered it in the fall, fabricated it over the winter, then the factory went out on strike. So we're sitting there, and the word goes up, everything's going to be delayed, and the head of the New York Yacht Club called the owner of the factory, explained what was going on. The owner of the factory crossed the picket line himself, hand carried it out, and shipped it to us. So it was manager, rich person to whatever talk. So it was, luckily, we got it. The extrusion was quite rough, and I need to fix that. It was ground. We had to grind it. The mounting holes had to be drilled and countersunk, and I remember that drilling operation was really a pain because titanium is sort of a gritty material, and we didn't have coated tooling in those days, and even when we tried cobalt tools, they didn't work as well. So I remember Ed was constantly resharpening the tool after every hole. I think we had to resharpen the tool after every hole. The countersink wasn't that bad. The other thing is that chips can catch on fire, so as the drilling went on, we needed to be water cooling the the milling machine. We did this on the milling machine. He did it on the milling machine. Next, oh, what happened? I went to the end. Sorry, gang. So, sorry. So this is the traveler track. When I was preparing this talk last week, I contacted the America's Cup Charters down in Newport, and he told me he had the traveler. Friday he drove it up, and it was sort of no ball bearings in it, rusty. I spent the weekend cleaning it up and shined it up, ordered a bunch of ball bearings, and now we have a working traveler here. The other point is these end stops is the one thing I actually built. So these end stops I built 57 years ago. But here we have on the table, and you can come look at it after the talk, the traveler track from 67, the end stops from 67, and the car from 70 with the stainless steel return races. And here's just some pictures of it from the top and the car at the end stop. And you see, somebody must have made a damn heavy jibe at some point and bent the main. I put it in my hand vise. There's no way I could straighten that out. So, the boom vang track. Now, the boom vang track was two parts. The boom vang system was comprised of two parts. A big U-shaped, it wasn't quite semicircle, they couldn't make it semicircle. It was more U-shaped, and a short track on the boom, and then there was a block and tackle between the two, so there was always a straight vertical line between the boom and the track. And with these, as I said, with these 2 degrees of freedom, the boom vang line was always vertical. I did the bending. Now, we had already set up a pneumatic press with curved jaws for bending aluminum track, but with this size track, we had to move the whole thing outside. I had to get sawhorse the whole thing's up outside because it's much bigger than the bender. And what we found out, what we sort of knew, was the titanium was quite springy. So the radius of curvatures of the jaws had to be kept making smaller and smaller to get the desired bend. And I think I spent at least one day, maybe 2 days, machining the jaws, taking it out, running the track through the jaws, checking it out, bend, change jaws, and I finally got it bent. And then it was installed. And then Edmund told them, look guys, this is going to stress your boom the way no other thing has ever stressed your boom. And in a heavy wind, you better ease that boom vang tension during a jibe so you don't break the boom, which they didn't do, and they broke their titanium boom, but they had a second one. So they learned their lesson. So this is a archival photo I found in the New York Times. This was Ted Hood's obituary. Showed this picture of Intrepid, and you can see the boom vang track right there. Now this is a photo op picture. If you look closely, there's a guy with a camera standing on the boom taking pictures there. But that is, you can see, that's the only picture I could find of, you could see the track on Intrepid. Now, as I said, the Traveler and the stop shackles had been developed before, but under the contract, these lightweight, very strong blocks were developed. So this is the last development effort I will talk about. The order was for on 10 of them, and they're used on the generator tracks, the main sheet system, and the boom vang, 8-inch diameter. Now the sheave was composed of an outer aluminum section and an inner stainless steel section, and the aluminum was drilled out to reduce weight. The main bearings, the needle bearings that were on the main load were 17.4 pH. Now, how do you put the stainless into the aluminum? Well, you use the fact of the temperature. The stainless steel interpiece was put on dry ice. The aluminum sheave was put in an oven and then taken out with tongs and dropped in. However, if it tilted at all as it went in, it jammed. You could never do it, take it again, so you had to machine off the outer aluminum, which happened a few times. Now, this sheave is for rope, but these were the days before low stretch line, so the Genoa sheets were actually wire rope and Dacron. And so the inner groove was for the wire rope, and the outer groove was for the Dacron, and the splice was placed such that when the Genoa was fully trimmed, the wire rope was just short of the winch, so the winch never took the wire. And again, I was the kid. The pros made these. I really wasn't involved in making these. This was beyond my skills. After that, he made a product line out of those. He made a big, they found that the 8-inch diameter was probably a bit big. They reduced it to 4, and he made a large boat design. We have an example here. And in the large boat design, it was all stainless steel cheeks, but it's still with the aluminum sheave with the stainless steel insert, no titanium, ball bearings and needle bearings. And then the small boat design looked quite the same, but was much simpler. It was a plastic, and then a stainless steel side to hold it. And just to show you what it was replacing, this is like a phenolic block from that era. There were no ball bearings. The sheave was just on a pin, and it was, big and clunky. But again, I couldn't find many more of these. They're all gone. So here's some archival photos. You can see the titanium boom being heavily bent by the traveler. You can see the track here. You can barely see the main sheet blocks in this picture. This was the cover of Sports Illustrated. And this is a picture from the race. That's Intrepid up there. This is Dame Patty, the Challenger. And it's hard to see, but I think you can see the main sheet on Intrepid is lower, probably because they could drop it with the ball bearing Traveler, and the boat doesn't appear to be as heeled over as far in this heavy air. So it's hard to know if that's me reading into the picture, but this is a picture of the two boats and Intrepid's in the lead. So the last thing was an experiment. Bus really wanted things simple, and all that main sheet line running around, he said, oh, can we make a simpler system? So Columbia was the trial boat for Intrepid, that when they went out sailing, and the Columbia was the 58 boat. And the idea was to put a one-part all-wire main sheet system on it. Run a wire rope from the end of the boom to a slot in the back deck to a Traveler located on the floor, and then underneath the cockpit to a cylinder winch down below, and you would call your commands for trim to down below. And the decision was made to test it out in Columbia. Now it was skippered by Briggs Cunningham, who was the skipper for the 58 Defense winner. But people know the name's Cunningham because of the Cunningham on racing sailboats. Now the Cunningham on racing sailboats is a system to control the main luff tension, underway without having to move the boom. And it was Cunningham who had the insight, this bit of history, that you could be done with Dacron sails. If you put a Cunningham on a cotton sail, it would just rip it. So that was a major breakthrough for Briggs, and that name is where it came from. So I went out, so I got to meet the gentleman. The hardware was fabricated. Edmund and I drove to Newport in the early summer. This was 1967. The bridge wasn't done yet. We took the ferry across, and Newport was a slum. It was really quite nearly scary. was 3 years after the riots had burned the city, and the efforts to restore the mansions, which we all know and love today, started by Doris Duke and Jackie O, had not yet started. So it was sort of, ooh. And we worked all day and late into the night to install this system. And here it is. There's the track, titanium track. Here's the car, phenolic return races. Here's the wire going up to the boom. Here's the sheave. And there's the wire going underneath the deck, and this is the wheel. Now look where that wire's going. Right underneath the deck. So we went out sailing. And I was stationed on the back deck to monitor the tension. We sailed up and down the harbor a few times, and never been on a 12-meter, and really never been much of a keel boat. I remember going upwind, and normally you look going upwind, you look there for the buoy. Oh, buoy's like up there. Oh, we'll tack and make it. And it was like, what? And it was like a real eye-opener. But what had not been appreciated with the new traveler system was the vicarious concern, or I would say terror, of a wire running below the cockpit floor. Everybody gingerly moved around so the wire was not directly below them. And the image of that traveler track breaking and the wire ripping up from the deck was just too scary. So nobody really thought of that before we installed it. Needless to say, they took that off, and that was never heard of it. That was the end of it. But it was an interesting experience, and I got to go sail on a 12-meter as a kid. So, in conclusion, Bus Mossbacher and his team on Intrepid easily won the 67 America's Cup, beating the Aussies 4 races to 1. It blew hard. In those days, the rules was everything had to be made in country. The Dacron didn't stand up, and after each race, their mainsail was each of their mainsail was in tatters. In 1970, Bill Ficker, who was a star world champion, and his team on Intrepid beat the Aussies in Gretel 2, 4 races to 1. Ed got the contract in 67 for the 70 defense. However, by that time, I was off to college. In the 1974 trials, Courageous beat Intrepid in the trials and easily won the cup against the Aussies in Southern Cross. The feeling was, given the difference in boat speeds, Intrepid could have won a third time. I have a vague memory of Edmund telling me he bid the hardware on Courageous but did not get the contract. Now, why isn't this company known today as opposed to Harkin and other people? In terms of boat hardware, he never set up high volume production lines and was late on deliveries. Sometimes I was caught in the middle of that. The introduction of the ratchet block really did an impact on his sales of his blocks, because that Harkin ratchet block was a revolution for those who know what it is, and he didn't have it in his product line. The other thing was the improvement in injection mold plastic. Harkin was able to introduce their line of ball-bearing travelers that now dominate the market. He shut down his business in 2010, at which point what was left, according to his son, who was here, he came up, are the large blocks for the 12 meters. So, I'll make some closing comments. So that useful experience, when I went on to college and graduate school, went to work. In fact, my first job after graduate school was at the Waltham Power Tube plant here. Having worked with those highly skilled workers and worked in sort of a blue-collar environment, I found it much easier than a lot of my co-workers to work with technicians, and that because I sort of spoke their language. And also I had an appreciation how highly skilled they could be. So that was, I think, a real help. Having that youthful experience was very helpful in the rest of my career. Now, my sister's an oral historian, and there's always a question of, well, people come up and tell stories. how true are they? So this is a lot of my memories. It's not factually, can't fact check it easily. But I did mention at the beginning that my brother and I started sailing Blue Jays in 1959. Well, I can prove that to you through, of all things, the New York Times. This is the Babylon Yacht Club in 1959. A photographer came up to me and started talking to me. My brother came over and snapped this picture. And in the New York Times, July 28, 1959, there I am. There's my brother. If you look down here, you can see on a string is the watch we use for timing the starts. So given that the New York Times confirms one of my earlier statements, by induction, everything I've said tonight is true. Okay? The next one is in 1983, I was working in Waltham here when we lost the America's Cup. And it bothered me a bit. But a couple of days after that, one of my coworkers came to me and said, "Alan, what's wrong? You know, what's wrong with you?" And I realized it had really gotten to me in a way no other sports event before, even with the Red Sox, before or after has gotten to me. It took me like a week or so to get over the fact we had lost. It was because, you know, I've been involved as a kid. Now, the last statement here. So I told you Edmund Laviano's grandfather built this house on this estate end of South House Point Road. And when he built it, the house actually had stables. The stables were the house up the road. And at some point, the stables were turned into a house, summer house, and sold off as a separate property. And in 1969, it was sold to a doctor from New York City, Dr. Zagnati, who had a daughter named Flavia, who I met through the Lavianos, who's my wife today. So, on that note, I'm done.
Questions? You need a mic.
I'm always interested in the creative process. Did Mr. Laviano on his own decide that sailing fittings needed improvement, or did sailors come to him and say, "Can you figure out how to make things better?"
No, I think being a sailor himself, he saw the need. He saw the need himself. You know, and if you ever had experience with those early cam cleats, you would have seen the need too.
So were those ball bearings captive, or were you always loading them, and if they came off the end of the track, would they go flying everywhere?
Oh, they would go flying. Both these designs, they'd go flying everywhere. So even though there were end stops, the instructions for both the large and small boat traveler said, your control line better limit the distance, because if you jibe hard and your control line isn't there, the end stop will just come. The car will just fly through the end stop. And then you just got ball bearings all over the place. And that's true of the Harkin design today, right?
There's a newer design.
Oh.
Captive, but yeah, that was a big part of it. Was you had the car that you had to load and
right, you had to load. Yes. And I loaded this car last night, or 2 nights ago, and it was, took some work. Yeah, we got a question here.
And I think there are some online as well. I'll go back for those.
What about low friction materials like ultra high molecular weight polyethylene or Teflon?
The problem is a saltwater environment. Okay, what happens is you're in salt water, and if that stuff gets in, and evaporates, you got salt. Now with these designs, which are relatively loose, you just wash them out. And so there was a reason why they weren't tight bearings, because if the track got tight, you just take fresh water if you had it, or salt water if it wasn't there, throw it on it, and it wash the salt out, and it would run. So you really didn't want a tight bearing, because if that salt got in, it would jam it up.
This is an online question. Was the invention of travelers driven by sailors or by engineers?
The inventions of travelers. So the question is, were the invention of travelers by sailors? I think it was driven by sailors, because you really wanted to have that mainsail control. So there were non-ball bearing travelers beforehand you could adjust, but you couldn't adjust them under load. So it was driven by a requirement for sail shape control, which is part of racing. You want to be able to control your sail shape under load. So it's driven by sailors, I would say.
Ask. Word?
I was a saltwater sailor in the 70s, and I can speak to the attempted use of Teflon. My sailing was a Hobie 14.
Okay.
And they went through a series of design innovations with different kinds of cars. And I remember putting in the shims of Teflon, which you needed to do about once a month.
Right.
Because just running the Traveler in fresh water, that wasn't even salt water, it would just burn through the shim, and you were back down to you're running on your car, your phenolic car again. So the Teflon idea on a Traveler was just almost a non-starter, even though there was a commercial product trying it.
Right. Well, but the Hobie was worried about cost, and to put a ball bearing Traveler on would have driven cost, I think.